Hi, my name is Alex Lopez, and this is my lab report for Physics 2212 Lab 4. The purpose of this lab is to predict the behavior of circuits containing resistors in series and parallel, and then use multimeters to measure the actual values of conventional current and potential differences in the circuits, and to examine the behavior of ohmic resistors and capacitors. And some of the fundamental physics principles used in this lab are Ohm's law, which is voltage is equal to current times resistance, capacitance, which is equal to the charge of the capacitor over the voltage, the loop rule, which states that the potential difference around a closed loop in a circuit is zero, and the node rule, which states that the current into a node equals the current out of it. So in this lab, we used an online simulator to model an ideal circuit, and the system is the circuit and the surroundings are everything else. And we're assuming here that there's negligible resistance within the wires and the ammeters. And for a brief preview of the results, the current in the initial 2 resistor circuit was 0.02 amps. The potential difference around the loop in the circuit was 0 volts, and the time for the RC circuit was about 6 seconds. The first part of the experiment, we made the circuit consisting of 2 1.5 volt batteries, 2 resistors. One was 47 ohms and one was 100 ohms, and 2 ammeters. And the current was calculated using Ohm's law, so combining the voltages of the batteries and dividing that by the sum of the resistors since they are in series, which gave us 0.0204 amps. And you can see the ammeter in the top picture shows 0.02 amps, so our calculation was correct. And when we flipped one of the ammeters, it read negative 0.02 amps because its positive and negative terminals were reversed. And when one ammeter was replaced with a voltmeter, the current on the other ammeter was 0, and the delta V was 3 volts because it was an open circuit, so there was no current flowing. So here you can see the voltage drop or potential difference from each point on the circuit. So from A to B, we gained 3 volts because that was going across the batteries. And then from C to D, it dropped 0.96 volts because that was the 0.02 amps times the 47 ohm resistor. And then from E to F, it dropped 2.04 volts because that was the 0.02 amps times the 100 ohm resistor. And the sum of the total potential differences is 0 because of the loop rule. So next we created a parallel circuit, and here you can see the reading on both ammeters increased to 0.06 amps because the current will only flow through the 47 ohm resistor, because when it reaches the node, it chooses the path of least resistance and avoids the 100 ohm resistor. Therefore, the total current in the circuit is 0.06 amps. And then you can see we calculated the resistance for each component. So like for the 47 ohm resistor, it was 0.96 volts, which is the voltage drop that we got in the previous slide, divided by the 0.02 amps, which is 48 ohms. And for the 100 ohm resistor, it was 2.04 volts divided by 0.02 amps, which gave us 102 ohms. And the differences there are just due to the lack of precision of the ammeters, but those are correct values. And then the wire and ammeter gave us 0 resistance. Next, we created an RC circuit with a battery, a light bulb, and a capacitor. And when the battery is first connected to the light bulb and the capacitor, the bulb starts out bright and then dims out over time as the capacitor charges. And then once the capacitor is fully charged, the light bulb is no longer emitting light and there's no more current flowing through the circuit. And then once the battery is disconnected, the bulb starts bright again and then dims out as the capacitor discharges. And while the capacitor is discharging, the current goes in the opposite direction compared to when it is charging. And so for the 10 ohm battery, I calculated that it took 6.82 seconds to charge and 7.4 seconds to discharge. And for the 20 ohm battery, it was 12.3 seconds to charge and 14.96 seconds to discharge. This is the data from the circuit with the 9 volt battery, 30 ohm light bulb, and 200 microfarad capacitor. And so you can see we have the graph of the ln of the delta V over delta V naught versus time. And the RC can be found by taking the negative reciprocal of the slope, which was negative 0.1667, which the negative reciprocal gave us 6. And the calculated RC was just the resistance times the capacitance, which was also 6. If we were doing this lab in real life and we're using a real ammeter, it would have a slight amount of resistance that was not accounted for in this ideal simulation. And if we had just hooked up a battery to a capacitor with no resistor, in the simulation it would have just immediately charged because there was no resistance. And in real life it would have taken a little bit to charge just because of the resistance in the wires, but it would have been much faster.